Chapter 10, Introduction to the Human Body, Part 7. Homeostasis and feedback. Homeostasis. Homeostasis is the condition in which a system such as the human body is maintained in a more or less steady state. It is the job of cells, tissues, organs, and organ systems throughout the body to maintain many different variables within narrow ranges that are compatible with life. Keeping a stable internal environment requires continuous monitoring of the internal environment and constantly making adjustments to keep things in balance. Set point and normal range. For any given variable, such as body temperature or blood glucose level, there is a particular set point that is the physiological optimum value. For example, the set point for human body temperature is about 37 degrees Celsius or 98.6 degrees Fahrenheit. As the body works to maintain homeostasis for temperature or any other internal variable, the value typically fluctuates around the set point. Such fluctuations are normal as long as they do not become too extreme. The spread of values within which such fluctuations are considered insignificant is called the normal range. So here we are. This is a thermostat. I have one of these in my house. It says it's old-fashioned. Oh well, but the thermostat is keeping the temperature in a building around a certain temperature. If it goes too low, then perhaps a heater will come on. If it goes too high, then the heater will shut off. Homeostasis is normally maintained in the human body by an extremely complex balancing act. Regardless of the variable being kept within its normal range, maintaining homeostasis requires at least 4 interacting components: stimulus, sensor, control center, and effector. The stimulus is provided by the variable that is being regulated. Generally, the stimulus indicates that the value of the variable has moved away from the set point or has left the normal range. The sensor monitors the values of the variable and sends data on it to the control center. So data is, maybe chemicals, maybe, a physical effect like heat. And this goes on to the control center. The control center matches the data, this chemical or temperature perhaps, with normal values. If the value is not at the set point or is outside the normal range, the control center sends a signal to the effector. The effector can be an organ, gland, or muscle, or other structure that acts on the signal from the control center to move the variable back toward the set point. Maintaining homeostasis involves feedback, which is a condition that sends a message back to control a response. Feedback can be the accumulation of a product or not enough of a product and can be influenced by shape changes. So if a product builds up and that product bumps in, for example, into an enzyme, that enzyme may cause a reaction to stop because its shape detects that enough of this product has been made. And then when the excess product falls away, disconnects from the enzyme, for example, then the enzyme might start making this particular product again. High body temperature may stimulate the temperature regulatory center of the brain to activate the sweat glands to bring the body temperature down. When body temperature reaches normal range, it acts as negative feedback to stop the process. So negative feedback means that it is a regulatory process, so that the whatever is it's being controlled around the set point, so that it goes a little bit up, a little bit down, but ideally will not achieve a range outside of the normal state. But feedback may be negative or positive. But all the feedback mechanisms that maintain homeostasis use negative feedback. So this is, again, a balancing, self-correcting type of feedback. Biological examples of positive feedback are much less common. Although they're natural, it's not considered to be the same as the homeostasis, which is that balanced state. The negative feedback loop. In a negative feedback loop, feedback serves to reduce an excessive response and keep a variable within the normal range. Both body temperature regulation and control of blood glucose levels involve negative feedback. So here we can see the stimulus in this loop is, for instance, the body temperature exceeds 37 degrees centigrade. The nerve cells in the skin and brain detect this, and then the regulatory center in the brain acts to activate sweat glands throughout the body. And now the sweat glands are cooling the body down. So we want to get in this range here, not to exceed the temperature of 37 degrees centigrade, but if it does exceed it, then we go through the same process again. So the body is constantly going through this, especially because when we eat food, we're burning calories, so to speak. When we metabolize glucose, there's a product of heat that results. And so our bodies can become overheated just from the metabolism process. So this is always being maintained here with the balance through signals through the skin and brain. The temperature negative feedback loop. Cooling down. The human body's temperature regulatory center is the hypothalamus in the brain. When the hypothalamus receives data from sensors in the skin and brain that body temperature is higher than the set point, it sets into motion the following responses. Blood vessels in the skin dilate to allow more blood from the warm body core to flow close to the surface of the body so heat can be radiated. As blood flow to the skin increases, sweat glands in the skin are activated to increase their output of sweat, which is called diaphoresis. When the sweat evaporates from the skin, it takes the heat with it. Breathing becomes deeper and the person may breathe through the mouth instead of nasal passages. This increases heat loss from the lungs. So you experience this after physical exertion, I'm sure. Temperature negative feedback loop heating up. When the brain's temperature regulatory center receives data that the body temperature is lower than the set point, it sets into motion the following responses. Oh, is it going to be here? Yes, here we go. Blood vessels in the skin contract to prevent blood from flowing close to the surface of the body. This reduces heat loss from the surface. As the temperature falls lower, random signals to skeletal muscles are triggered, causing them to contract. This causes shivering, which generates a small amount of heat. The thyroid gland may be stimulated by the brain via the pituitary gland to secrete more thyroid hormones. This hormone increases metabolic activity and heat production in cells throughout the body. Remember, when metabolic activity produces heat just normally, and if it's accelerated, then more heat is produced. In other words, you're burning more food. The adrenal glands may also be stimulated to secrete the hormone adrenaline. This hormone causes the breakdown of glycogen, which is the carbohydrate used for energy storage in animals, to glucose, which now can be used as an energy source. So this catabolic reaction, breaking a large molecule down into smaller molecules, produces heat. So it certainly plays a role in this negative feedback loop. Here's the glucose negative feedback loop. In the control of blood glucose level, certain endocrine cells in the pancreas called alpha and beta cells detect the level of glucose in the blood. Then they respond appropriately to keep the level of blood glucose within the normal range. If the blood glucose level rises above the normal range, pancreatic beta cells release the hormone insulin into the bloodstream. Insulin signals cells to take up the excess glucose. And this will then occur until the level of blood glucose decreases to the normal range. So the idea is to keep the blood glucose within a normal range. If the blood glucose levels fall below the normal range, pancreatic alpha cells release the hormone glucagon into the bloodstream. Glucagon signals cells to break down stored glycogen to glucose and release the glucose into the blood until the level of blood glucose increases to the normal range. You might be wondering why this is so important. It's because that in order to nourish the cells of the body, there has to be the right amount of glucose in the blood, not too much and not too little. A lot of glucose in the blood can actually damage vessels because it acts like it's kind of like it's sharp. It can actually cause damage to vessels. And of course, if the cells don't get enough glucose from the blood, then the tissues will starve. The positive feedback loop. In a positive feedback loop, feedback serves to intensify a response until an endpoint is reached. Examples of processes controlled by positive feedback in the human body include blood clotting and childbirth. Blood clotting. When a wound causes bleeding, the body responds with a positive feedback loop to clot the blood and stop blood loss. Substances released by the injured blood vessel wall begin the process of blood clotting. Platelets in the blood start to cling to the injured site and release chemicals that attract additional platelets. As the platelets continue to amass, more of the chemicals are released and more platelets are attracted to the site of the clot. So the platelets are acting like a type of a glue almost, that they're sticking to the injured area and also sticking to themselves. So the positive feedback accelerates the process of clotting until the clot is large enough to stop the bleeding. But it's not regulating it to a corrective level, right? It goes in one direction. We're not seeing the wound start to heal and then come back and stop healing. That would be a negative feedback loop. To get put the platelets in and take the platelets out, that's not what's happening here. The platelets have to keep amassing until the bleeding is stopped. The positive feedback loop, childbirth. The process normally begins when the head of the infant pushes against the cervix. This stimulates nerve impulses which travel from the cervix to the hypothalamus in the brain. In response, the hypothalamus sends the hormone oxytocin to the pituitary gland, which secretes it into the bloodstream so it can be carried to the uterus. Oxytocin stimulates uterine contractions, which push the baby harder against the cervix of the uterus. In response, the cervix starts to dilate in preparation for the passage of the baby. This cycle of positive feedback continues with increasing levels of oxytocin, stronger uterine contractions, and a wider dilation of the cervix until the baby is pushed through the birth canal and out of the body. At that point, the cervix is no longer stimulated to send nerve impulses to the brain, and the entire process stops. So it's actually like when the head of the infant pushes against the cervix, it's like a mechanical thing. The nerves are being activated, and they then cause a reaction in the brain. When homeostasis fails, homeostatic mechanisms work continuously to maintain stable conditions in the human body. Sometimes, however, the mechanisms fail. When they do, homeostatic imbalance may result, in which cells may not get everything they need or toxic wastes may accumulate in the body. If homeostasis is not restored, the imbalance may lead to disease or even death. Diabetes is an example of a disease caused by homeostatic imbalance. In the case of diabetes, blood glucose levels are no longer regulated and may be dangerously high. Medical intervention can help restore homeostasis and possibly prevent permanent damage to the organism.